we go. All right. So today's lecture is kind of important in the sense that this is the last topic that I'll include in the first exam. So anything after today's lecture is not going to be in the first exam. So, sorry. And I'll give you guys a practice exam next week, and then the actual exam is going to be 1 week after the practice exam. All right? Has anyone went to the shared folder and just kind of explore and try to find out what's in the shared folder? Some of you. Okay. So I encourage that you go to the share folder, which is here, and go to. There are many files. I mean, you're more than welcome to explore. I mean, these files are all intended to be shared with you. Otherwise, it wouldn't be in the share folder. But there's one folder particularly called OX1. I just use X1 to represent exam 1. So when you double click on that one, it will give you exams, from the past of this class. So 1-1, okay. So the 116 is 2016, and 119 is 2019. Okay, and then the 3 is spring, the 9 is fall. This is the internal code for Los Rios. So when we name a semester, that's how we internally code a semester. And I just chose to use the same code, to indicate which semester that exam was from. Okay. And so, these are all exam 1s, and you can definitely just kind of go over these actual exams from the past, especially the one that I just uploaded, which is this one here. This is from the previous semester, from spring 2019. So something that you can do, kind of over the weekend. I'm not going to go over this today because, when I go over this exam probably on next Tuesday, that means the following Tuesday is going to be your actual exam 1 date. Is that okay? So your actual first exam 1 date is going to be 12 days from today. Yes?
Do we have any lab on exam day?
Yes. So technically we still have lab, but usually what I do during the lab time is to tell you guys what the answer is or the key of the exam. Yep. All right, so do we have any questions about this? Yeah, let me close that. If there are no questions, we're going to move on to the last topic that we'll go over before exam 1. It is very much related, and this is kind of why I want to include that topic, because it is still related to binary subtraction. So this is the module of binary subtraction. We are pretty much done with this binary subtraction module, okay? So now the question is, well, how do we compare? In other words, if I give you one binary number, I give you another binary number, can you tell me whether the first is less than the second? And that's all I care, whether one is less than the other. And you might ask, but then what about equal to? What about not equal to? And so on. So I'll go through a very quick conversion table so that we are convinced that we only need is less than, okay? We don't need the other comparison operators at all. So let me, I think mousepad is still up somewhere. I'll just pick up that one and get rid of everything here. Okay. So let's start with x is less than y, okay? X is less than y is exactly x is less than y. Because remember, we want to convert everything to be only expressed as is less than, but we can also use Boolean operators. Okay, so we can use and or not, okay? But we want to use only less than as a relational operator. So the next one is going to be super duper easy. What if the original expression is x is greater than y? No, you flip the sides. Y is less than x. Okay, very good. So here's a little bit trickier one. What if the original one is x is less than or equal to y? then it becomes, it is not the case that y is less than x. Does that make sense? Let me just check myself. Yep, seems to make sense. Okay, next one, x is greater than or equal to, x is greater than or equal to y. Well, that's pretty easy because we got the other one, so it's just the flip side of that one. Is that okay? And I'm pretty sure it's being recorded, so if you have to choose whether to listen to me and understand what I'm saying in class versus copying everything down on your notes, you know how to make that trade-off, okay? But I'm just confirming that we are recording. Okay, next. Let's do something that's trickier, okay? What if the original one is x does not equal to y? What do you think? And we can only use less than, but we can also use Boolean operators, logical operators.
An or.
We can use an or, very good. Okay, so what do we put on the two sides of the or? X is less than y on one side, and y is less than x on the other side. Very cool. And the last one is x does equal to y, and that becomes what? The negation of that, exactly. And of course, I can do this a lot faster than you can write. But the idea is that, okay? The idea is really simple. It's just like, well, if you know how to express not equal to, then equal to is really just the negation of that. Is it optimal? No. But it does make the point that, hey, we don't actually need the other comparison operators. Less than or equal to, greater than or equal to, greater than, equal to, not equal to. Those are all unnecessary. Now, you might have to think about this a little bit, and we go like, but Tech, you also said something about not and or are also not necessary. All we really need was NAND. And you're absolutely right. So we can actually convert everything to just NAND and less than. Isn't that cool? So next time you turn in a CISP 430 homework assignment, you can use a program to do that conversion, and then turn in the code that only makes use of less than and the NAND operator. And I would like to see the expression on your professor's face. It's like, oh, what is this? This is what I learned from cisp310. Yes?
I'd rather turn it into all less than and NAND statements than map it out in transistors and then turn that in.
Well, you can't really specify transistors in C and C++, but you can definitely define NAND as either as a macro or as an inline function. So are we sufficiently convinced that is less than is all we need? We're good? Okay. So next, let me show you where the notes is, okay? Because I do want you to make sure everybody knows where to find note. So let's see, which tab should I use? Yeah, this is a good one. All right, so we are now down to here, binary number comparison, because we were done talking about signed value representation too. That's the previous class. We talked about 2's complement, and if you have read the notes, you would know what is 2's complement. It really is just a fancy name of taking the bitwise knot and then adding a 1. I'm pretty sure we talked about that one. The tilde symbol, tilde x plus 1, and that's how we do negation. Okay? Any vague recollection that we did that?
Yeah.
Okay, very good. I just want to make sure, okay, because I cannot really tell when I first looked at you guys. Okay, just want to confirm. All right, so this is the next topic, which is binary number comparison, which is also what you'll be doing in today's lab. So in today's lab, we're going to look at binary comparison. Did I click on the wrong thing. There we go. Oh, the next one. I thought it would give me the tab. It would make the most recent tab the current one. Anyway, so section 2 is just a repetition of what I just said. Okay. So you can either use this or you can use the other one. It's basically the same thing. So what we'll do now is to move on to section 3 and talk about unsigned number comparison. Okay. So in unsigned number comparison, okay, this is all just kind of mathematical basis of what is handy to know. Okay. So it starts off with these two axioms. Does anyone want to disagree with these two? 0 is less than 1 is true, and 1 is less than 0 is false. Can we say that this is like, okay, this is axiomatic, we don't question that? Okay, we good? We good? Okay. So now we want to look at what if we have a binary number that is interpreted unsigned. What is the value represented by a number that is represented in base 2, and we want to interpret it as an unsigned number? That's the question. So the first question we want to ask is, can we prove this? Okay, let me zoom in a little bit because that might be helpful. There we go. So just the highlighted portion. Can we prove that 2 to the power of n is greater than the summation of all the smaller powers of 2? Now in this case, I started with 0, but we can actually start off with negative infinity if you want to. Okay, it doesn't really matter. Now, does it make sense? Let's think about it. Okay, it seems to make sense, right? Because 2 to the power of 3, which is 8, is greater than the summation of 1, 2, and 4, which are the lesser powers of 2. Because 1 plus 2 plus 4 is 7. Not quite there at 8 yet, right? What if we include all the fractions? 2 to the power of negative 1, which is half. 2 to the power of negative 2, which is a quarter. Even if you include all of those, all the way to infinity, it will come pretty close to 8, but it will never be 8. It will approach 8, exactly, as your lower bound keeps going lower and lower. Okay. But can we prove it? It's a very good observation, but can we prove it, right? So what is next is really just a proof. And I am going to bypass the actual proof for now. Okay. So the proof is just this part here, and it's proof by induction. Okay. So let's just say that we are done with this proof, and we have established that for any n, this comparison is always true. Is that okay? Right? It sounds really trivial, but it's actually important. So what we do next is to apply that. So now we want to use, this notation is actually not really used in the description, so we can just ignore that. So you're given two binary numbers. One is x and one is y, and we know both of those numbers have m bits, so they're all m bit wide. We can assume that after this m, xi and yi are the same, they're all zeros. Okay? In other words, I give you two 32-bit numbers. But the idea is, after bit 32, okay, including bit 32, all of those other digits to the left-hand side are assumed 0. It's really just like, how do you write out 123 in base 10? 1, 2, 3. Why don't you write it out as 0, 1, 2, 3, or 0, 0, 1, 2, 3, or 0, 0, 0, 1, 2, 3? Because those leading zeros do not add anything to the interpretation of the number. So it's just extra, and we don't need it. And that's what it's basically for. What this part on the screen is saying is, after a certain point, we just assume all of those more significant digits are zeros. So we don't need to consider those. Are we good so far? Yep. Okay. So what we'll do is we're going to say for some I that is greater than p, so we're going to use the notation xp dot 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 0 to represent the part of x that is going from x to bit p only. Okay, so it's just a notation. We are just trying to say which part of the binary number are we concerned about. Okay, it's from bit 0 all the way up to bit p when we use this particular notation. So what we do is now we say we can now make an assumption of if I is greater than p, we assume xi equals to yi. In other words, we are scanning a number from the left, from the more significant digits, and everything is matching at least down to bit p. Yes?
So it's basically like a for loop where it just goes through
Yeah.
each
Each
bit
digit.
P, and then because P would be the
Yes.
the
So
bit.
p is kind of like a variable in the loop. So it goes, from the left, it goes from a high number, and we keep scanning to the right-hand side. So we are scanning from left to right.
And we're waiting until 1 is 0 and 1
Exactly, until we can come to a conclusion.
Okay.
Okay? So we can basically say that we start with p being infinite or a really big number, but until we get to m, they're all zeros. So we can say, okay, but they're all the same. We cannot tell which one is bigger. Okay? So from that point on, we just say, okay, what if we get down to a point where we have not established that they are equal? Okay? Then what do we do? So what we do is we then look at xp and we look at yp. Okay? If the first one, if x is 0 or xp is 0 and yp is a 1, then we know as an entire number x is less than y because all the more significant digits are identical. Is that okay? All right. So if we get into the second situation where x1 is 1 and y1 is, xp is 1 and yp is a 0, then we know x is less than y is false. Okay, now, yes, I know you guys can say that, but we also know that x is greater than y. I don't care. I just need to know whether x is or is not less than y. As long as I can come to a conclusion of whether x is or is not less than y, I'm done. I don't need to know whether y is greater than x. Okay? And if you repeat this and you get down to, if you match all the digits and p is now 0, then x is less than y is false because we have no other digits to help to differentiate which one is larger. Okay? So it really is not different from how you would do a comparison between your two base 10 numbers. Okay? If I give you two really long, messy, base 10 numbers, how do you compare? You start with the most significant digits. Does that make sense? And you scan your way to less significant digits until you find a difference. If you cannot find a difference, the two numbers are the same, then the first being less than the second is false. So this works out exactly the same way as how you would do it in base 10. So now the next question is, okay, so if this is the mechanism of comparison in terms of by hand, okay, using a loop, how do we do this, using a computer or using circuitry? So I'm moving on to this paragraph at this point. What I just described above makes sense because that's what we do in base 10 too. We all know how to do that. The question is, do we need to create additional circuitry to perform comparison? And the answer is no. So we already have the correct mechanism to do it using the existing subtractor that we have. Yep.
Can you explain the else statement?
The L statement?
After p equals 0. Go back to the first step, but decrement. P minus
After p equals to 0.
1.
Here?
Yes. Can you explain the...
Oh, you mean here?
Yeah.
Oh, that's just p equals p minus 1. P gets p minus 1. We are decrementing p.
But
Because if p does not equal to 0, then we can decrement p. We are moving one digit at a time.
Oh, that's okay. Got it.
Yep. We're moving one digit at a time. So you start off at, you probably will start off at digit m minus 1. And then if that digit, does not, if the two digits xp, yp are the same, then these conditions will be false. They will all be false because at that time p is m minus 1. It's not 0 yet. Then you decrement p by 1, and then you go back and then you redo the whole thing until one of those three conditions becomes true. Okay, that's a good question. Okay, moving on to this part here. So this is a statement. This is what I claim. Okay, now in this notation, v of x, v of y is the value of x, the value of y. Remember, x is a number. It is just a bunch of zeros and ones. So v of x is saying, okay, the value represented by x. V of y is saying the value represented by y as unsigned, using the unsigned interpretation. I have to use v of x and v of y here because when x and y represent signed values, then it's no longer clear, are we just looking at the bit pattern or are we looking at the interpreted value? So v is the interpreted value, in this case unsigned. So this statement says v of x, the value of represented by x, is less than the value represented by y if and only if Tm is 1. Well, Tech, you never introduced what is Tm. I did in the previous module. Actually, 2 modules before this one. What is T in a subtraction? Take, which is the borrow, right? The borrow bit. So the number that we're concerned about only has m bits, which means if you look at the difference after a subtraction, it only goes from bit 0 to bit m minus 1. This is the extra one that is hanging around. Now, you guys are all either working on or are done with the 3x3 carry look-ahead adder, right? Remember your K3? This is the equivalent bit, but in a subtraction. This is the one leftover borrow bit that is not a part of the answer, but is hanging around. Is that okay? So this is really it seems to be pretty profound because it's basically saying with the current subtractor that we have, okay, we already have the mechanism of determining whether the first number is less than the second number by just looking at the overall borrow after a subtraction. I think this is really cool because it means I don't have to derive any additional circuits. We already have the mechanism to tell whether the minuend, which is the first number, x, is less than the subtrahend, which is y, the second number. But it only works for unsigned interpretation. So the rest of this part here is basically just a proof. Okay, so the proof is, it starts off with a review of what is a borrow bit or take bit. Okay, ti plus 1 equals to the b, the borrow, of xiyi, or the borrow of qiti. I certainly hope this looks familiar by now. After the carry look-ahead homework assignment and all of that discussion, I really hope that this is now familiar and go like, okay, what is this doing in here? Well, we'll go ahead and use the same kind of a loop concept, and we make the same assumption. We assume that xi equals to yi, those bits are the same for all of, and ti equals to tp, for all the I greater than p. So we basically look at the subtraction and we scan again from the more significant digits to the less significant digits. And we say, oh, okay, everything from here to here are the same. Okay, so now the next question is, what are we going to do next? Well, once again, we scan to a point when xp equals 0 and yp equals 1, then we can come to a conclusion. Remember, that's an easy case because now we know x is less than y. But the question is, are we guaranteeing that the overall borrow would also be a 1? Because that's what we want to know, is whether the overall borrow is telling us whether the first number, x, is less than the second number, y. Okay, so we plug it in. So if xp is 0 and yp is a 1, we plug it in and we say the borrow is going to be a 1. Is that okay? Just because of how the borrow bit is defined, t subscript p plus 1 is guaranteed to be a 1. Is that okay? But if t subscript p plus 1 is a 1, by the first assumption here, we also know all of the other borrow bits are 1s, including t of m. Is that okay? So this part here is already telling us that, yes, if x is less than y, then we guarantee that t of m is going to be a 1. But that is not sufficient, because if I only have this guarantee, then it leaves open the possibility of in some cases, even if x is not less than y, the borrow bit is still a 1. So I have to show that no, if x is not less than y, the borrow bit have been a 0. So I have to go through that process as well. So we go to the second case. What if we find that xp, yp are different, but this time xp is a 1 and yp is a 0? Remember, everything to the left-hand side of digit p are the same. Okay, so you have to remember that assumption. Okay, so we work this out. If xp is a 1, yp is a 0, then qp is guaranteed to be a 1. Remember, this R function is just exclusive OR. 1 exclusive OR 0 is a 1. So we guarantee that qp is a 1 in this case. Then t subscript p plus 1 is guaranteed to be a 0. Is that okay? That just has to do with how the take bit or the borrow bit is defined. Oh, if t p plus 1 is a 0, and we already have this assumption that all of those other borrow bits to the left-hand side of p are the same, that is also going to be telling us that t of m is also going to be a 0. Is that okay? So right now we have proven that if x is less than y, the borrow bit is going to be a 1. If x is greater than y, the borrow bit is going to be a 0. We have one last case left, which is, what if they're the same? Because we don't want the borrow bit to be a 1 when x and y are the same. So we have to prove that that does not happen. So now we look at the last case here. What if p equals to 0? Well, if p equals to 0, then we are looking at t0. T0 in your circuit is an input, but unless we are doing a multi-digit or multi-word subtraction, T0 is assumed 0. Okay? Well, if T0 is assumed 0 and all of the other borrow bits are the same as T0, doesn't that tell you that T of m is also going to be 0? All right, so we have handled all three cases. The only time T of m is a 1 is when x is less than y. Okay, so this is kind of a loose proof. It's not a really kind of formal proof of everything, but it is a very loose interpretation. But it does reason out, why it works. So the conclusion is it shows that if the borrow bit Tm is a 1, it tells us that x is less than y. Yep.
Also, I wonder if you recorded. I tried to follow on your way here, but the stream wasn't up, so.
It is because it's listed as private.
Okay.
Yep. So it's not public.
Afterwards? Okay.
It is posted afterwards. Yep. Just in case I need to bleep out portions of the lecture. So far I haven't really needed to do that, but there's always that chance.
Covering your ass.
Yep.
There you go. There's the
there's a bleep moment. But
I have a question.
yes.
Is there a more efficient way to do this? Because it seems like in half the cases where x is greater than y, it's done really quickly, but then it takes a really long time.
Nope, it takes the same amount of time as a subtraction. All right, well, let's try this out a few times. Okay, so we'll go to Notepad here and we'll just try a few examples. Okay, now remember this is unsigned interpretation. All right, so we'll use one pretty extreme case of let's try out 0, 0, 0, 0 minus 1, 1, 1, 1. Okay, so just to remind you what the terms we have been using are, this is x, but in this case it is also known as the minuend. Okay, this is y, but we also want to call this the subtrahend. Because I don't want to call, the first number versus the second number in the subtraction, so I'm going to refer to their formal name in the subtraction. This row has no formal name, I call it Q or partial difference, but you don't have to use that. This is our traditional T, which is the kind of the borrow bit, but I don't use borrow because the borrow, B is used as a function name. And this is our difference. Okay, so only the first, second, and the fifth row have actual formal name. The other two rows are just for intermediate results, so they don't really have a formal name. So we'll go ahead and carry out this calculation, but this time I'm not going to use arithmetic concepts to carry out the calculation. I'm only going to use logical concepts to carry out these calculations. 0 exclusive OR with 1 is a 1. 1 exclusive OR 0 is a 1. Then we look at 0 and not 0 and 1 is a 1. Not 1 and 0 is a 0. So now we have, sorry about that. Okay, maybe I use this one. So we have 1 or 0, which is a 1. That one goes here. Are we good with this? This is how we define t I plus 1, using column I. Is that okay? All right?
It was y or t?
Huh?
It was y or t to get the...
No, it is not x and y, or not q and t. This bit is the negation of this and this, the whole thing, or the negation of this and this. Okay. Okay, we'll work out this one here. 0 exclusive with 1 is 1. Okay, in fact, I can do it in any order. 0 exclusive with 1 is 1. 0 exclusive OR with 1 is 1. Okay. 1 exclusive OR with 1 is a 0. And then over here we have, okay, let's try to figure out this bit. Okay. So this bit being a T2 is not 0 and 1, which is a 1, or not 1 and 1, which is a 0. So we end up with a 1 or 0, which is a 1. This is the same scenario, okay? So I'm not going to repeat saying that. And now we have 1 exclusive OR with 1, which is a 0. And then we have 1 exclusive OR with 1, which is a 0. But we are missing the most important part here because the overall borrow is what we want to look at, okay? Because now that becomes the star of the show, okay? The extra, in addition, or subtraction, which is the bit that's just hanging around, we don't know what it's for, is now the star of the show, okay, in the subtraction. So we want to figure out what this guy is. Well, we kind of know what it is already, right? Because we have done this many times already. In fact, right here we have done it like at least 3 times because it is not 0 and 1, which is a 1, not 1 and 1, which is a 0, and then we OR those two, which is 1 or 0 in this case, is a 1. That is important because in this case, we have a borrow, the overall borrow being a 1, okay? You can call it T4 4 in this case. T4 is the overall borrow. It is a 1. That tells us that the minuend is less than the subtrahend. I do not look at the difference. The difference doesn't tell me anything about the ordering between the minuend and the subtrahend, but the borrow bit does. Is that okay? Now, this example is particularly useful because of some additional concepts that we'll go over today. Okay, let's look at the other way around. Okay, we got 1, 1, 1, 1, minus 0, 0, 0, 0. Okay. Do you want me to go through the long version or the short version? Long version? Okay, I can go through the long version, but I'm not going to spell out everything because this one is a lot more trivial than the other one. Can we agree on that one? Okay. Can we agree that that is the case? And can we agree that this is pretty much the same for every single column? Yes? Okay. Then can we agree that this is going to be a 0? Okay, well, that's easy. So what is this telling us? Okay, T4, the borrow of bit 4, which is the overall borrow of the subtraction, is a 0 this time. It's telling us that x is less than y is false. Now, by this alone, it doesn't tell us whether x and y are the same. It only tells us that x is not less than y. That's all the borrow bit can tell us, is it is not less than. It can be greater than, can also be equal to. Are we good so far with this? Seems pretty easy. Okay? It also kind of makes sense at a very intuitive level because there's a reason why we call this bit here the borrow bit. You don't borrow if you already have enough. You only borrow when you don't have enough. Kind of makes sense, right? Okay. So now we are done with unsigned interpretation.
Wait, you
Yeah.
didn't show an example where they're equal.
Well, if you want an example where they're equal, change these to all ones. Then what's going to happen? All of these become zeros. Oops.
I mean, but how does it know that they're all equal? Is the question I was getting.
How? We don't. That's the whole point. If you only look at the borrow bit, we do not know that the minuend and the subtrahend are the same. We only know that they are not the minuend is not less than the subtrahend. That's the only thing we know if you only look at the borrow bit. But remember, we don't need to tell the other ones because all we care is whether it is less than. Because we can replace all of the other comparison operators with less than and a bunch of other logical operators. Okay? So we are moving on to the sign interpretation now. And okay, so we'll take a look at this derivation. I'm not going to go through each row of the derivation. We'll just go from the first to the last, okay? The first one here is the value, signed value this time, represented by a bit pattern x. So x is still just a bunch of zeros and ones, okay? X itself cannot be negative because x is really just a bunch of digits, zeros and ones. V of x, on the other hand, is the signed interpretation of the bit pattern x. That can be negative or positive. Are we clear on that concept? Okay? So this boils down to the last row. We only focus on the last row. What is the last row telling us? I think by this time we know what the sigma notation is and how to interpret the sigma notation. Yes? Okay. So what is that telling us? Uh-oh, I forgot to bring my power supply, and I got enough time for this class, but the next class is I have to go back and charge my computer. After this class, we're good. Okay, so what is this telling us?
We start at n minus 2.
we stop at m minus 2, not m minus 1, which is m minus 1 is really the last bit, okay, the most significant bit. But we only stop at m minus 2 because what we do with m minus 1 is a subtraction. In other words, we add up the least significant, all of the less significant bits except for the sign bit. So we add up powers of 2 corresponding to those bits. And then we say, well, we're going to subtract the power of 2 corresponding to the most significant bit, if the most significant bit is a 1. Okay? So it looks kind of, icky. I can give you an example. Examples always help to clarify this stuff. So let's just say that we want to take a look at the value, okay, signed value, represented by the bit pattern, okay, 0, 1, 0, 1. Okay, it's a 4-bit pattern. Okay, so in this case, it is going to be 1 plus 4, and that's it. Because the most significant bit, which is bit 3 in this case, it corresponds to the quantity of -8. But it's a 0, so this is all we get, which is 5. Okay, so we say this is representing 5. And then we look at another one, which is, let's say, 1, 1, 0, 1. Okay, looks kind of the same, except for the sign bit, right? So this one is going to be 1 plus 4 minus 8. Why do we have a minus 8? Because the most significant bit, bit 3, is a 1. This guy is a 1. But using the sigma notation or the expression that we just looked at, we do not add the power of 2 corresponding to the most significant bit. We subtract that power of 2 from the rest, which is our minus 8. Okay? So now you have 1 plus 4 minus 8, which is -3. Then you ask, well, is that actually true? Because I think in this class we only used a number wheel that has 8 slots and not 16, right? Fortunately, when I talked about the same concept with the other class, I used a number wheel that has 16 slots. Very handy. So we look at this and go like, okay, where's 1101? Right here. What is it representing? What is the signed value it is representing? -3. It works out. Okay? So are we good so far with this expression here? Okay, all right, cool. So now we have a theory. Okay, so I hope this derivation does not surprise anyone. X is less than y if and only if x minus y is less than y minus y. Does anyone want to argue? We have a scale. It's tipping this way. If I take away the same amount of mass on either side, the scale will keep tipping in the same direction. Does that make sense? Does, right? Okay. But wait, y minus y is guaranteed to be a 0. In other words, I have nothing on this side of the scale. It's tipping this way. Does that make sense? Okay. But this is saying that x minus y is less than 0, right? So it's telling us the difference is less than 0. Well, anything that's less than 0 is also known as what? Negative. Very good. Wait, I think we have a bit that tells us the sign of a number. What is that? It's called the sign bit, right? And where is the sign bit? The most significant bit. Wow. So this seems to suggest that we can use the sign bit to tell us whether the minuend is less than the subtrahend in a signed comparison. Are you guys following what I'm saying? Okay, let me say that one more time. If you follow this logic, which is totally just completely mathematical, x minus if and only if x minus y is less than 0, or the difference is negative, x is less than y. Okay? It makes perfect sense, right? But if the difference is less than 0, it means the difference is negative. If the difference is negative, then the binary representation would have the sign bit being a 1. So this is all pointing to the direction of, hey, with signed comparison, we just look at the sign bit of the difference after subtraction, and that is going to tell us whether the minuend is less than the subtrahend. Okay? It makes sense up to this point, right? Okay? And it does make sense. It actually does work half of the time. Okay? So I'll show you examples of when it works and also when it does not work. Okay? So I'll show you a case when it works. 0 and 1, okay? Because I don't have to do it again. See how lazy I am? Right here. This is an example. Oh, wait, is that the one? Nope. Oh, this one works too. Yeah, we'll work with this one first. So let's work with this one here. I don't have to do all the computation. I know the sign bit is a 0 already. Yes? Because this 0 here is in fact the sign bit. It's the most significant bit of a binary number. That's the sign bit. Okay? So if the sign bit is a 0, it would suggest that the minuend is not less than the subtrahend. Yes? The minuend, or the value represented by the minuend, is not less than the value represented by the subtrahend. Does that make sense to you? Okay, so let me emphasize this is unsigned. So in this case, we have D3, which is bit 3 of the difference, which is also known as the sign bit of the difference, is a 0. Okay, it shows us that it is not the case that x is less than y, but this time we are using the signed interpretation. Does that make sense to you? In other words, the key now is what is the value represented by x and what is the value represented by y? It's okay, the laptop is still up. It's just that the cable is loose. I still got 22% of battery left, which is according to the what? Go ahead.
X is 0, but then y is going to be -1.
Y is -1, exactly. So 0 is less than -1 is false. Does anyone want to argue with that?
I was confused for a second until you said signed.
Signed, yep, exactly. So this is why, okay, I used the y here. This is why y is tricky. Because 0 is always 0, okay? If you look at the sign interpretation, 0, 0, 0, 0 represents the quantity of 0, no problem. If you look at the sign interpretation, 0, 0, 0, 0, it's also representing the value of 0. So it is the same in both cases. 1, 1, 1, 1 is not. 1, 1, 1, 1 unsigned is representing what again? You add up all the powers of 2, there's no subtraction. So we got 1 plus 2 plus 4 plus 8, which is 15. But what about the signed interpretation of 1, 1, 1, 1? 1 plus 2 plus 4 minus 8, which is -1. Okay? So that is why, it works out in this particular way. Okay, let's look at the second example, okay? Because I'm lazy and I'm just reusing examples here. So in this one, we have D3, bit 3, which is the most significant bit of the difference, which we also call the sign bit after a subtraction. This time it's also a 0. Okay, it tells us that it is not the case that x is less than y. But now I have to emphasize the first one is using the unsigned interpretation. The second one is using the signed interpretation. Does that make sense? Well, let's check, okay? Using the signed interpretation, 1, 1, 1, 1 is 1 plus 2 plus 4 minus 8, which is -1. Same with the second row. And we say -1 is not less than -1. And as a result, hey, the sign bit is correct. Are we good so far? What about the unsigned interpretation? Using the unsigned interpretation, the first number, or the minuend, is 1 plus 2 plus 4 plus 8, which is 15. so is the second, right? 15 is less than 15 is false. But is our borrow bit this time telling us that result? Yep. So even though we look at the borrow bit for unsigned interpretation and we look at the signed bit for signed interpretation, in this case, they both tell us the same story, because regardless of whether it's signed or not, a number cannot be less than itself. But this is a good way to check, right? A sanity check, just to make sure that these particular ways of interpreting the result after subtraction does work out. Are we good so far? Okay. Remember, I said it works half the time, so the other half of the time, it does not work. So I'm going to show you an example where it does not work. Okay. So we'll have this one. Okay. It doesn't have to be exactly this, but I'm just going to use this one. So we'll work out the actual result of the subtraction first, and then we'll look at the sign bit and the borrow bit and see whether each one makes sense or not. Okay. So I'm going to do it really fast this time. Okay. This is 1, 1, 0, 1. This is assumed 0. This is 1. This is 1. This is 1. And that's going to be a 0. That's a 1. That's a 0. That's a 1. That's a 0. Okay. So we look at the result of this subtraction. And we try to look at T4. What is T4 this time? It's a 0. Okay. That is telling us that x is less than y, unsigned is false. Does that make sense? What is the unsigned interpretation of 1, 0, 0, 0? 0 plus 0 plus 0 plus 8. So that's just 8, right? What is 0, 0, 1, 1? Is 1 plus 2 and then nothing else, which is 3. So now the question is 8 less than 3? No. Is the borrow bit telling us the same answer? Yes. Well, the borrow bit is a 0. It tells us that x is less than y is false. So it's telling us the same thing. It's consistent. It's all good. What about the sign bit? So let's check that out. So we look at D3, which is the sign bit of the difference. And that's also a 0. Okay. So that is telling us that the signed interpretation is also not less than. Whoa, hold on a second here. That doesn't seem right. Okay. Because 1, 0, 0, 0 as a bit pattern is representing what when we use the signed interpretation? -8. Because we have 0 plus 0 plus 0 minus 8. We subtract the power of 2 corresponding to the most significant bit, which in this case is a 1. So the minuend is -8 this time. What about the subtrahend? Subtrahend is still 3. Signed or unsigned interpretation, it's still 3. So now the question is really asking, is -8 less than 3 in signed interpretation? And the answer is yes, but the sign bit is saying no. So the sign bit somehow is not giving us the correct answer. Okay. There's another way this can go wrong. So I'll give you the other case when this can go wrong. Just give me a moment to remember how that works. Oh, okay. Yeah, that's it. Okay. This will be a pretty easy case to work with. But it does illustrate the other case when the sign bit is not going to tell us the actual result. Okay. So once again, I'm not going to spell out the actual subtraction. Okay. But this one is super duper easy, right? I mean, Okay. All right, so now that we have the result, we're going to ask the question again. What is T4? T4 is the overall borrow of the entire subtraction, and it is a 1. It is telling us that using the unsigned interpretation, x is less than y. Does that make sense? Okay, what value do you think 0, 0, 0, 0 is representing? Oh, 0. What about anything other than 0, 0, 0, 0 in unsigned interpretation? It has to be greater than 0. So it doesn't even matter what the second row is. Doesn't matter what the subtrahend is. As long as it is not 0, it's going to be greater than 0. But, okay, let's look at this specific case. 0 plus 0 plus 0 plus 8 is just 8. So the question is 0 less than 8? Yes. Is the borrow bit telling us the correct answer? Yes. Okay, not a problem. What about the sign bit? Okay, we look at D3, which is the sign bit of the difference, and it is also a 1. Okay, it's telling us that x is less than y signed. But is that right? 0 is still 0. Our minuend is still having the value represented is still 0. But what about the value represented by 1, 0, 0, 0 when it is interpreted signed? It's negative 8. 0 is less than negative 8. 0 is less than negative 8 is false. But the sign bit is suggesting the opposite. So the sign bit is wrong. Is that okay? So why? Because mathematically, we just went through the proof. This should have worked, but it does not. Why do you think that is the case? So to understand why it is not working, we have to look at the actual result, okay, the actual difference. So when we look at this difference here, okay, when we look at, okay, so let me just kind of spell this out a little bit more. This is the subtraction of negative 8, okay, I'll use parentheses, is negative 8 minus 3 in the signed interpretation. But what is the result? If you just look at the difference, 0, 1, 0, 1, what value is it representing using the signed interpretation? It's 1 plus 0 plus 4, which is 5. Does that make sense to you? I start off with a negative value, I subtract a non-negative value from it, and I end up with a positive value. Does not make sense, right? Now, why is it not making any sense? Because what it is supposed to be? What is supposed to be the correct result? Negative 3 minus negative 8 minus negative 3 is negative 11. Okay? Okay. Find negative 11 on this disk for me. It's not there. We have the difference of that subtraction has exceeded the ability of a 4-bit number to represent. That is why the difference is wrong, because we don't have enough bits to represent that actual number. Is that okay? In other words, we have an overflow situation. Okay. What about the other scenario that in which it also did not work? Okay. Yep.
Wait, never mind. I can see it now.
Okay, so in this scenario, it also did not work. Why is it not working? If you look at the sign interpretation, this is 0 minus negative 8, which would have been 8, positive 8. So you go like, well, I vaguely remember 8 is on that disk. You're correct, it is on that disk. Except that slot is taken up by negative 8 when we choose to interpret bit patterns as signed values. Is that okay? See here, even though it does have an 8, but it also has a red negative 8. The red negative 8 is saying, if you choose to interpret this bit pattern in a signed way, it can only represent negative 8. Okay, so that means if you use signed interpretation, the range is only going from -8 to 7. 8 is not one of the values that can be represented by a 4-bit signed integer. So once again, we have an overflow situation. The result is too big, or it is exceeding the range of values that we can actually represent. Is that okay? All right. Okay, so, okay, I get it. Okay, so that means every time we have an overflow situation, the sign bit is going to be wrong. So all we need to know now is, are we having an overflow situation? Does that make sense? Okay. Now, as it turns out, to know whether we have an overflow situation or not, turns out to be a pretty easy thing to do. Okay. So what I'm going to do is I will say, let's look at a more abstract subtraction. Okay. This is the minuend, so I'm going to say m, and then I don't even care what these are. Okay. They can be whatever. Doesn't matter. This is the subtrahend. I'm going to use s for now. So this s is not sum, it is subtrahend. And this is a subtraction. And then we have this, I don't really care. So I'm just writing out all the bits, but most we don't care anymore. Don't care, don't care, don't care. And even the overall borrow, we don't care at this point. So let's just put it here, but it's not our concern. And I'll call this D, because it belongs to the difference. Okay. So we'll focus on just this little picture here. Okay. From only these 3 bits, I can tell whether the result of a subtraction is overflowing or not. Okay. So let's think about the 8 different scenarios. Okay, because we have M as D. 3 independent variables. Well, so it seems they're not actually completely independent. Okay. And then we try to look at, actually, yes, okay. Okay, we'll say does overflow, question mark, okay? 0, 0, 0, okay? If all 3 bits are zeros, do we have an overflow? Let's see how we interpret that situation. When they're all zeros, that means we have a non-negative value minus a non-negative value, ending up with a non-negative value. Does that make sense? 5 minus 3 is 2. Are we good? Okay. So that means we do not have an overflow. Okay, we put a 0 here. What about 0, 0, 1? We have a non-negative value minus a non-negative value, but the result is negative. It can happen. 3 minus 5 is negative 2. Yes? Okay. So no overflow situation. It can happen. 0, 1, 0. Do we have an overflow situation? We are subtracting a negative value from a non-negative value, ending up with a non-negative value. This is the way it should be. Because when you subtract a negative value, you're adding to the minuend. So if the minuend is non-negative to begin with, of course it should stay non-negative. Is that okay? So there's nothing wrong with this scenario. No overflow. 0, 1, 1. You're subtracting a negative quantity from a non-negative quantity, but the difference is negative. I think we have a problem. Right? Okay? So we have an overflow here. 1, 0, 0. Do we have an overflow? You start up with a negative value, and then you subtract a non-negative value from it, and you end up with a non-negative value. Do we have an overflow? Yes. Okay. 1, 0, 1. You have a non-negative value to begin. You have a negative value to begin with. You're subtracting a non-negative value from it, and you end up with a negative value. Does it make sense? This is the way it should be. Okay, so of course there's no problem with this. So no overflow. 1, 1, 0. You're subtracting a negative value from another negative value, and the result turns out to be non-negative. Can that happen? -1 minus -3 is 2. Okay, it can happen. So no overflow in this case, 1, 1, 1. You are subtracting a negative value from another negative value, but the result is still negative. Can that happen? Yeah, it can happen. You can subtract -1 from -2, then you end up with -1. Okay, it can happen. So no overflow in this case. Oh, look at this. Do I have a way to specify overflow as a logical expression? You go like, oh, isn't this a little bit beyond what we can handle in this class? No, you guys can do this. If you can handle exclusive OR, you can handle this. Because we only have 2 rows where the results are 1s, right? So give me one conjunction where this row is going to give us a 1. Just in terms of MSD, negations, conjunctions, disjunctions, and whatnot. I just want that expression to be a 1 if and only if M is 0, S is 1, and D is 1. How would you do that? Remember the exclusive OR expression. We're just going to extend that approach a little bit. What about something like this? I negate M, conjunction with S, conjunction with D. Would that do the trick? And are you convinced that this expression is a 1 if and only if M is 0, S is 1, D is 1? For all of the other rows, it would be zeros, right? Because it targets, okay? If you look at this conjunction, each term of the conjunction targets the very specific case of this row. Are we good? What about the next row then? The next row also has a result of 1, and I just want a single expression that will be a 1, but only for this row. What do you think that would look like? Yep, M, not S, not D. Oh, but wait, Tack, we need both rows to be 1s and not just one of these rows. So what do I do about these conjunctions? Put an OR. Just OR them, right? So overflow is now defined to be not M, and S, and D, or M, not S, not D. And instead of writing overflow, computer science people like abbreviations, so it's just O. Okay, so this is called the overflow flag, but most of the time it's just represented by either an uppercase O, which is difficult to look at because it looks like a 0, and that's why in some other literature it is also using just a V because it's the second letter of overflow. So when you see the O or the V flag, it basically means overflow. Are we good? Okay. I'm looking at the clock because I really want to finish this discussion. So now we take this, okay, and we say, woohoo, let's apply this to things that we already have worked out, right? Let's put it here. And I'm just going to put it everywhere, and then we'll do the computations, when we get to those points. Okay, this one and this one here. Okay, so we'll work on the first one first. And we say, okay, in this case, what is overflow? What do you think? Does it meet one of these requirements? We have this is basically saying 0, 1, 1. This one is saying 1, 0, 0. It doesn't meet one of those cases, does it? So that means overflow is going to be a 0. There's no overflow. Okay. And when there's no overflow, the sign bit is correct. Yes? Remember, the first 2 examples, had the sign bit telling us the correct result. Okay? Okay, I'll just emphasize that. Okay? What about the second case? In the second case, actually this one does overflow. How do we know it overflew? Because this is M, right? Okay, so M is here. This is S. Not S is a 1. Okay, this is D. not D is also a 1. We got 1 and 1 and 1. So it meets one of the conjunctions. It makes one of the conjunctions a 1. So the overflow is a 1. Okay, so we say this is a 1. And we also have to remember to say this is incorrect. Okay. Oh, okay. So when there's an overflow situation, the sign flag is incorrect. Okay, at least in this case too. Let's work out the next one. So the next one, let's work out the overflow flag first. Does the sign bit of the minuend, subtrahend, and the difference meet one of the requirements? And if it does, which one is it meeting? The left or the right? The left. Very good. Because M is this bit here, the negation is a 1. The subtrahend and the difference, they already have 1s. Okay, see this one and this one here. So we now end up with 1 and 1 and 1, which is a 1. So we end up with 1 or 0, which is a 1. So we do have an overflow situation here. Is the sign bit incorrect in this case? Oh, okay. So this is still supporting our conjecture that whenever the sign bit is incorrect, overflow happens. Whenever the sign bit is correct, there's no overflow, right? So let's work out the first one. I think there's this one. Okay, I forgot about this one here. So let's work out this one. Is there an overflow situation? We got 0, 1, 0. Okay, we got 0, 1, 0. So if you plug in 0, 1, 0 here, the conjunction gives us a 0. If you plug in 0, 1, 0 here, it also gives us a 0. So we end up with 0 or 0, which is a 0. There's no overflow. Okay, but was the sign flag correct in this case? The sign flag was actually correct. Cool. So there's something between the sign flag and the overflow flag. If we somehow combine these two, then we have a conclusive correct answer of whether the minuend is less than the subtrahend. Are you getting that idea? I hope so, because that's what we are leading to, and we'll come to that conclusion within 5 minutes. Okay, so one way to look at this is to say, okay, the sign flag lies when the overflow flag is a 1. Okay, so one way to look at this is to say that. Okay, all right. So now we have 4 different scenarios. We have the sign flag and the overflow flag, and then we have, okay, so tell me, is the minuend actually less than the subtrahend? Subtrahend, there we go. Okay, so we got 4 scenarios, 0, 0, 0, 1, 1, 0, and 1, 1. Okay? Okay, so let's look at the first one. The sign flag says, nope, it is not less than. And then the overflow says, the sign flag is lying. So if the sign flag says no, but it's actually lying, what is the actual result? Is the minuend less than the subtrahend?
Yeah.
Let me say that one more time. The sign flag being a 0 means the sign flag says, nah, the minuend is not less than the subtrahend. Then the overflow comes along and says, no, he's lying. So what is the actual truth? It is less than. Let me see. Let me think about this. No, I take it back. No, because I forgot about the 0. Okay. The sign flag said it is not less than, and then the overflow said the sign flag is not lying because there's a 0 here. I take it back. Okay? So what is the actual truth? It is not less than. Okay. Sorry about the confusion. I was thinking about the next row already. Okay. Here is the next row. The sign flag says the minuend is not less than the subtrahend. And then the overflow flag said, nope, the sign bit is lying. What is the truth? It is less than. Okay, very good. Okay, next row here. The sign flag says it is less than, and then the overflow said that the sign flag is not lying. So what is the truth? It is less than. Okay. And then the last row is the sign flag says it is less than, and then the overflow said the sign flag is lying. What is the truth? It is not less than. Oh, exactly. We have seen this again and again. We saw this the first time when we looked at the result of addition, adding 2 bits, the result of adding 2 bits. The second time we saw this was when we subtract 2 bits, right? The result of subtracting 2 bits. And we see this again. It is exclusive OR. So this is telling us that the minuend, okay, signed, okay, I'm going to make this extra clear here. A signed minuend is less than a signed subtrahend, if and only if the sign flag exclusive OR with the overflow flag. Okay. Now, if I just leave it like this, it should be sufficient, but this makes it like super duper clear. It's kind of like, in C and C++, you have a Boolean expression, and then you equal to true. It's redundant, but it doesn't hurt. Okay? Is that okay? So in this class, we have a special name for the result of the exclusive OR. I call it the L flag. And can anyone try to think of why I call this the L flag? Huh? Less than, exactly. Not lie, less than. Because we talked about lying earlier. No, but it is less than. But it's only using the signed interpretation. The borrow bit is useful for unsigned comparison, and the sign flag is the L flag is useful for signed comparison. Are we good so far? We still have some time left, I think. So let me give you one last thing, because I do want to. Yeah, we got 2 minutes left. So let me give you one last thing, because we have been working with a lot of pine needles. Okay. So what is the conclusion of this? The conclusion of all of this is when you do need to make a decision, based on the comparison of numbers, okay, which happens a lot, right? Because when you write your C and C++ programs, every time there is a branch, the decision-making process usually involves some kind of comparison, right? So when you need to make that decision, that is the only time you need to know, oh, are we dealing with signed numbers or are we dealing with unsigned numbers? That's the only time you need to know whether you should look at those bits as signed interpretation or unsigned interpretation. Okay, let's say you know which way you should go. Okay, I should look at this as signed interpretation. But remember, it is the same subtractor that is doing the comparison. Okay, you use the same subtractor whether they are signed or unsigned representations. So what is the difference? The difference is what flag do you pay attention to? Do you pay attention to the borrow flag, the borrow bit? So when I say a flag, it's really just a bit, okay? So are we looking at the borrow flag or are we looking at the L flag? That choice is based on whether the numbers are signed or not. So it all boils down to the choice between L versus B when we talk about signed versus unsigned. When you're adding, it doesn't care. When you're subtracting, it doesn't care. When you're comparing, it doesn't care. But when you need to interpret the result after a comparison, then you have to make the right choice. Is that okay? So I'm going to emphasize this point as appropriate later on in the semester. In about week 8 or so, we'll start to get into assembly language actual programming, the whole thing. That is when you need to you need to remember what we talked about today, because when you choose the instructions, some instructions pay attention to the L flag, some instructions pay attention to the B flag. That is when you need to say, oh, I need to remember, is this memory location storing a signed value or unsigned value? Then you make the right choice, okay? But when we get to that point, I will remind you, okay? Today's lab is based on, the flags. So, you might want to kind of read the notes a little bit too, alongside when you're doing the lab. But I think the lecture covers everything already.